So we're back. We're back. We're back. Portfolio multiverse. Yeah. So we're back. These I got to rename. So I'll call these portfolio Chicago. Good. Where did we leave yesterday? So basically, what we want to do is we want to uh, we're building this thing with SymPy, right? Multiverse computing, the paper, this one. So I guess I've downloaded it so many times that I probably yeah. So we're basically building this part in here. Exactly. Good. Let's zoom it in. So and so what I was trying to do last time was basically to kind of build that programmatically as a, so build the actual equation using symbols like with SymPy, right? And I think the issue that I was encountering was that, sorry, I'll run this. And the issue that I was encountering is that I cannot, like, it didn't seem like I could use symbols like these. Um, mhm. So R is not defined. Symbol R. R is not defined. What is not defined? This is not defined. I was giving it a try, like if whether I could just like substitute this thing like that. Where is not defined? R. Substitute R. Can I just like, can I concatenate strings? So I think I'm doing this wrong. So how would I build that? Like, how does this work? Like so SymPy build expression and loop. Like, can I just not construct an expression like these? So I get the symbols. What is this expression? Nice wrap expression. X symbols X. Maybe I just have to. Okay, maybe I just have to use these like that. I'm just like using the wrong. It still complains. Okay, can only concatenate strings, not insta strings. But that seems like I should be able to build things like these, shouldn't I? Like, if I so let me just let's just so I'll just comment the whole thing. So this is the symbol R. Like, can I just make an expression? Like, can I just say like print print these, right? Yeah. And now I say print these plus 2. Yeah. So that works. So can I use a variable? Maybe I can't use a variable. That's the point. Or no, that works. Okay. Okay, that works. It's using floating floats, but it shouldn't be a problem. Now, if I have an expression, so this is expression, right? And now I do expression equals expression plus, I don't know, another symbol, right? Say P. And now it's going to complain. No, it didn't complain. And so I can now print these P plus R. So if that works, why doesn't it work this way? So I have these. So I have these, and I create these WNT, which is basically 1k, 1 divided by k plus the symbol R. And then what I do is I tell it like just 1 divided by k. Maybe, so maybe that's what doesn't work. Let me just go back for a second. So if I just go and say 2, no, that works. I mean, come on. Oh, what am I doing? So that works. So why doesn't this work? So 1 divided by k plus sp symbols are not plus. We're not plussing here any symbols. So this is what we have, and then wnt equals wnt plus plus or times, sorry, and then basically you have like okay, no, what I should do is I should basically have sort of the temporal expression. Okay. No. What I should have in here is I should have basically so the qubit expression, it's basically can I just do like qubit expression equals 0, right? And then say qubit expression. This is a bit hacky, but like qubit expression is equals qubit expression plus, and then I do with the symbol xntq plus 2 to the power of q, right? Times. This is what I'm going to have to implement now. Exactly. That's what we're doing. So 2 to the power of q times the symbol x and tq. And so we're adding these, and then we have this q expression at the end. And what we do is w nt equals, yeah, well, I don't have to actually define it here, so I can just say 1 over k times Q expression. There you go. That should work. And so this is W and T. And I can actually go and print W and T now, and let's see what we have. Why? Can concatenate string, not into string. Where is this happening though? This is the problem probably. Oh, come on, like how do I Python concatenate string and int? I thought you just could do that like that. Yeah, just using the string function. String y. Okay. Maybe there's a way to just evaluate these things in there. There you go. Invalid syntax. Invalid syntax. Is it the name of the variable? Oh no. Or why is it invalid syntax? Why is it invalid syntax? I'm gonna put a letter or something, or what is the... Or here I'm missing... Oh, sorry. There you go. Yay! Finally, 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 finally. Maybe I just like... Maybe I won't... Oh no, I should add this because if we have numbers bigger than 9, like we're gonna get into trouble otherwise. Okay, now we have it. So now we have all these things, right? For basically the 6 qubits. Those are the 6 qubits that we want to have. And if I would say NQ is 2, then what we're gonna have is this basically. Nice. So each row, like it represents, like each 2 qubits represent then 1 asset. So 6. Because I have 3 assets and 2 time steps. Okay, I like it. Now, so now we have these, right? Now the question is, how can we use SymPy with arrays? Can you just like, can you do that? Like, can you do, for example, because now we have these, right? So this is basically equation 25. Is it? Yeah, this is equation 25. And so WNT is equation 25. I mean, for each, yeah. So equation 25 is without, so it's not these, it's these, equation 25, right? The thing what we're doing here is now we have to, so now we're in the loop here where we iterate over t. So we have WNT, and so what we need to construct in here is okay, so maybe what we should do is we should do it differently. So no, wait a second. Wait a second. Mm, do we want to have everything in one array or not? We don't. So there's no, well, there is actually t in here. That's what makes it confusing. That here is per time step. So once we're in one, yeah, we're in one time step. But then we need to have for all the assets, that's n. So what we need to have now is, what do we need to do? So now I would put this into a vector, right? And that will be then wt. So I would just basically say, so we've got wt and now like wt append wnt. And now I will just print these. No, not really append. NumPy. Should is here. NumPy quotient array, append array. Yeah, you don't do it like that, of course. Append wt, so wt equals wt. There you go. Okay. Empty array. Like how do you do that? So okay. I can just do that. Can you just do that? Yeah. Don't know what this is though here. Like if I print it in here every time we, okay, these, yeah. Okay, cool. So we have this array, like what is the print, what is the length of this array? 4. Why? We want nq to be 1, we want this to be like that, and so still 4. Let's have, it's an empty array, and we should be, we also have wnt, then we should append this to wt. Yeah. WT, oh, WT, that's wrong. It's WT, yeah, I don't know what I'm doing. 4 and 4, as it's 2 times. But like, yeah, so we have these WT that we've built now. Now this WT, right? Like it's it's for all the assets. So now we have it, and so what we have to do here is we start building the actual equation. So we have to do this minus mu, right? Transpose of minus these. So actually, if I go and we'll just pick these things, right? So forecasted return is this, and then we'll just you know, prepare the data here. So forecasted return is this. We're only gonna basically what we're gonna do is we're gonna, like, what I want to try to do now is say, okay, so I'm WT, and what I do is I do so the H is basically going to be an expression that it's like 0, right? So that's the Hamiltonian. And so what we're now going to do is we're going to do what we want to do is now I have WT defined. It's here defined. That's the thing. That's what I'm doing wrong. So WT is defined here. And so it's an empty array. No, that's correct. It's not defined. We're filling it up here. So now we are here, and so we have the array with the WT, which is like an array. So now what we have to do is we have to do like NP transpose of -1 times the F return, right? Because we're going to have this minus in here, times WT. And this is basically what the Hamiltonian is going to look like. So exactly. And then we're going to define the next WT. Yeah, that makes sense. And so if I print H, what do I have? It's going to be broadcast together with shapes 3, 2. Okay. So I think that it's complaining about these. So what these is basically, oh yeah, sorry, it's time, it's like T. What I should do is yeah, you're right. So I should actually, it should actually be like these. Yeah, exactly. So what we do is we actually have to, it's the return for that time t. What we're looking for, I'm going to print h, still not working. So now we have going to broadcast together with shapes 3, 4, 3 assets. So we have 3 assets, but then WT how many assets? It's got like how many? It's got 4 elements, and that's what I don't understand. It should have 3 elements, right? Where's that 4 elements? So you're going in here, Q expression 0. So you're adding the symbols. You know, it's just 1. Then you're doing 1 over the K times the Q expression. And you're appending it. Yeah, well, because we have 3 assets, right? So we have 3 assets. So So if we have 3 assets, WT should have, yeah, 3. I don't know why. I was, with the empty, I was creating sort of, okay, maybe that was the problem. That makes more sense. And now this should work. Okay, and now I'm happy because I think it works as I expect it to work. So it's really multiplying all the coefficients and all the stuff as they should be multiplied. That's good. Good. So for t, so print for like print t, right? Print. So for t0 you have these, for t1 you have these. Why you have more stuff for t1? I don't know. To be honest. T1. I know you don't have more. No, you have 3 elements, and here also have 3 elements. It's just these elements have. It's interesting. Is this correct? Oh, it's got to have, yeah, it's kind of 6 elements because, well, because you're adding like, yeah, you're adding 3 more exactly. So if I was not doing these, then yeah, makes sense. Okay. So the final H is what we care about. I like it. Cool. So the final H is what we care about here. Exactly. So that's H. Okay, cool. So now we've done with this component here. Yeah, I think that's easier to do it this way. Now the next thing you do, right, is this constant in here, like we'll call it the risk. So we'll have the risk, which will be like whatever, right? Like I'll just define like one over half, like just half. But this is basically this here, and so then we kind of have. So we need the covariance matrix of the assets, and this is kind of the covariances that we have in here. So this is this matrix. Covariances, those are the returns, those are the covariances of, we'll call it co for short. It's random stuff. And so what we now need is, I like it because now it allows me to actually build that step by step. So I do H plus, and I'm doing this part in here. So it's your risk times NP transpose of WT, right? Times the covariance matrix times WT. Nice. Yeah. Oh yeah, look at this baby. Cool. Cool. Why did it print it 2 times though? Why did this print it 2 times? Because H is just, do I have a print statement here somewhere that I can see? No. Oh, it's not 2 times, it's 1 time, I think. It's 1 array, just, or, I don't know. But you see this, like there's square components. Like, do we have so far like quadratic components? I don't see any quadratic component. Like, I don't see any quadratic component. I see squares, but I don't see quadratic components. Like that doesn't count as quadratic. That's the point. Okay. Good. And now we're gonna have to basically do this last part, because the last one we'll leave for the next episode, because basically what we'll have to do with these is we'll actually have to do some kind of Lagrange stuff with SymPy. Can you do Lagrange multiplier with SymPy? Probably you can. Lagrange's method. Oh no, that's something else. Or it's oh, there you go. Lagrange multiplier examples with SymPy. It's perfect. Perfect. Then I guess we'll just yeah, we'll just get that done. But we're here now, so we have the lambda, which we also were gonna make up. Lambda. I'll just call it lambda L. It's basically going to be np random rand. Can I just like, is it just print L? Does this print just a single number, random? Yeah. Okay, cool. So this is L, and then okay. So then we've got this difference. Now, how do we do this? So this is WT plus 1, right? This is WT plus 1 minus WT. That's the point. It's so this part in here. I was not quite sure about like the approximation here. They approximate these by these parabola. So with the transaction costs in there. But still they square it. So this is the optimal parabolic coefficients for the transaction costs as discussed above. Finally, let us mark that into setting the percentual profits. That's the percentage of return minus the percentual costs. Okay, yeah, sure, but like, so this means I have to calculate that kind of, that basically sucks because I'm at T now, right? And what I should do is now how do I build this? Because I'm looping within T. The different time things, right? And I'm adding these to the overall age. Doing for t equals 0, and then I'm going to do this for t equals 1. But here I kind of have to take a look at one step ahead, right? See, this is confusing me a bit because there's no definition, so it seems to be useless to me right now. because I really want this to correlate to t plus 1. And so that part here. So what I gotta do now is I actually gotta probably do a nested loop in here. Or I should get out of the loop now, actually, over t already. Right, so I'm here now, and actually I should simply I should do what is written here, right? So t plus 1. So I should basically iterate over t, right? So I should iterate over t. Then I should iterate over like 0, 1. What should I do? I should iterate I should just have t plus 1. Yeah, basically. I should actually do like these, because you should iterate always for, you know, the 1t. Essentially what I want to do, right, is I want to copy these, which I should probably probably encapsulate into something that returns an expression. Generate. So generate wt, and then we give it a t, right? And so what this is really doing here is def generate wt, and it has a parameter t, and it's kind of doing this, and then it's return wt. So this is what it's doing, generate wt. So we're generating this expression. Okay, it needs to have n, it needs to have nq, n and nq only, k, and k. So it needs to have n, nq, k. So it generates that expression. And so what we now need to do is I need to kind of take these and basically say, well, we now kind of have the tx expression equals 0, and so we're going to have to do is tx expression equals tx expression plus, and we want to generate how does it look like for what is going how can this, so how's this going to look like for t's? This is in between each consecutive step. Like, what if t is bigger than 2, right? What are we gonna get? So How long are we gonna have? 40 minutes. Okay, cool. So if this is gonna have, so we're gonna generate WT, and then we're gonna have, and we're gonna do like, so TT plus 1, right? And we're gonna generate then T. So this is kind of what the expression is gonna be doing. So it's gonna be doing all these squared, is it? Yeah, because essentially what this will mean is that, like, for step t, we take a look at the difference between t plus 1 and t. So for step t plus 1, we'll take a look at the difference between t plus 2 and t plus 1. So if you have like bigger t's, right? So I think that it's, and each of those should be actually multiplied by this lambda, and this lambda, this L, right? So this actually will be L times these. And then, and so now I will have the expression for all, like across all the t's. And so what I can do is I can just say h equals h plus the tx expression, I think. I think that's about right. And now I have basically this component here. And maybe I shouldn't, maybe I should really go one step forward, not square it, but like, because I really want to see I really want to see the actual quadratic terms. Let's see what we get here if I do this. Valid syntax. That's not possible. Well, it is possible. Okay, cool. Yeah, we don't see the quadratic terms because it's just not unpacking these. Whereas if I take the whole thing and kind of multiply it by itself, then what do I get? Do I get I also don't get a quadratic terms, I just get that multiplied like that. I actually would like, yeah, okay, but if now, for example, I ask for the, let's say, coefficient of the term, like I could ask the coefficient of the term x0. Guys. So how was that again? To get the, sorry, expression coef, okay. It's not really coef. Why is it an array? NumPy. Oh, because it's so it's not like if I work with arrays, like, give me a second. Something's just bothering me right now. What is this going on? Yeah, whatever. So, there's someone calling. So I'm not getting what I want. I'm getting the array multiplication, right? And I would like to expand this. Am I getting the array multiplication? If I was now print h, right? Yeah, that's the problem. I'm getting the array multiplication, right? Like, what is these? That's not what I expected. So I'm getting like a long array. It's like a hmm, hmm, hmm. Why am I getting arrays? Like that's the point, is like I don't know why I'm getting arrays. I want to multiply arrays and then actually just get the uh, SymPy. You know what I mean? Expressions with arrays. Of symbols. And a symbolic expression. That's not what I want to do, so metric symbol. No clue how to convince SymPy to use one-dimensional arrays using only one index. Matrix. So is the answer. Since your list X is numeric, you don't need a symbolic sum to handle it. Just sum the list. No, that's not, I don't think that's what I want. So, SymPy equations with vectors, for example. Vector math. Okay, so that's what we, vectors and scalars, that's what we probably needed. Okay. SymPy vector. So actually I have to probably create this not with a NumPy array, but like with a vector. Any examples though? SymPy vectors. Because then it's not a pen. What we have to do is physics vector module. So, okay, so I'm mixing NumPy, and that's the wrong thing to do. Okay. So something like this. Okay, I don't know. Matrix transpose print B. It's column vectors or row vectors. Okay, so what this is telling me is that what I should be doing is not appending here anything, but like I have WT, and then I should return, maybe I can return it as a SP matrix. what if I of like one row? So if I just go ahead and do these, let's say print w underscore t, it prints the matrix. Okay, nice. Okay, that seems to work actually. That's nice. Okay, so and then it's not transpose. What I have to do here is I have to do sp transpose. That's confusing. Of -1 times. So the minuses I should add in here basically. What I should do is I should do -1 times these. So I should just generate it like that, and then I don't like that though. No, I don't like that. So I should do it like this. W's like this, and then what we're doing is -1 times the transpose of the returns. Times WT. Transpose of these returns. But then the thing here is I should declare that as a matrix as well, right? Because I want to use it as part of my expression. So I should also declare these, it's complicated, times WT. And then I should change these as SP transpose of WT times the covariance, which is actually a matrix. So I should also define it as SP matrix of these covariances, and then times WT, which is already a matrix. Class, yes, I knew that would break. Cannot add class immutable dense matrix and class int. Where is this happening? Here. Maybe I don't have to declare this as matrix. That would be quite magic. And so I would actually do these in p transpose. Maybe just don't have to. Oh no, in this case I do have to, because that's, but I don't have to do these. Here I'm transposing the returns. Okay, good. I'm not gonna leave it here because I'm running out of time actually. But I've moved quite forward now. So I've basically, I think I got it almost right. I just need to figure out the right way to build the expression. And then once I have the expression done, basically, I'll be able to just query, each of the different terms, and because I know where they go in the matrix, and because I know where they go in the matrix, I can say, hey, okay, expression, give me the coefficient of that particular, component, and then that's it, and then we're done, and then we're done with the matrix. But it's a tricky thing to do to build that up. I mean, we'll have to do the step in between here where we actually calculate this Lagrange thing. Yeah. Okay, cool. But it's tricky to actually. Otherwise, I wouldn't know how to do that. Like, it's almost impossible to do this in a, I would say, more or less programmatic way to then kind of scale it to all the different comparisons that you want to have. You're gonna have to create it this way. I mean, it's Cool. I hope you're enjoying this. I'm learning a lot. So SymPy, NumPy, and all this other kind of stuff, and that's definitely helpful.